Okay, so what we're going to do today is called analysis of variance, which in my thinking is an unfortunate name. It's also called ANOVA. And you can take entire courses just on analysis of variance. We're going to do what's called one-way analysis of variance, and it obviously can get a little bit more complicated than what we're going to do. But even though we are going to calculate a variance, this test is to look at means. The difference when you have more than two means. Actually, you could do this instead of the two-sample t-test for that matter. It's really any time you have more than one. If you see things where people do it, they will do this, then a two-sample t-test, and then once they get to three, they'll use analysis of variance. So just to give you an idea of what analysis of variance is, this is just some data. 3 groups, 5 numbers in each. So in the first group, Group A, whatever that is, there was a 9, 3 10s, and an 11, and so on. And what I want you to notice is that we have these 3 means here, and you can tell that these 3 groups differ because they're distinct. There's no overlap. If you told me there was a new, whatever this is, a new person came in and they had a score of 20, I can tell you which group they're in. They're in group 3, or that's what I'm going to predict. If someone comes in with a score of 16, I'm predicting that they're in group 2. So what we're really looking at is 2 things, and you'll see a ratio. We're going to look at the difference between these 3 means. And so that's it's going to be called mean square treatment, but it's just how far apart are the means. And if you think about what we've been doing, the two-sample t-test would be just like this, except for we just have 2 groups. So one of the things we look at, remember in the numerator, was x bar A minus x bar B. Now the formula is going to look a little bit different. Well, it's going to look a lot different, but it's just looking at difference between the sample means. Okay? And I kind of already said it, but okay, I guess I have to get rid of that. What I have now is, with the white boxes, is the other kind of variation within each group. So when we were doing the two-sample t-test, the width of those boxes, where I have the arrows, that's what standard error measures. So on the top, we would have difference between means, and on the bottom, how much variability within each group. So here's another example, a different problem. And what I want you to first of all notice is that the means in the samples are exactly the same. They're still 10, 15, and 20. But there's a lot more spread within each group. So it would be more difficult. If someone came in and said, well, I have a score of 18, could have been an 8. That's in the range of all 3 groups. It's more difficult for me to predict which group it came in. In fact, you can't really make a prediction at all. It doesn't. In other words, in the first problem, knowing their score, you can tell which group they're in. Well, by contrast, if you knew which group they're in, you kind of have an idea. You can estimate what their mean's going to be, or what the value is going to be. Whereas in the second example, there's so much error. That's what standard error measures, is within each group how much variation is there. And so, we can kind of use this as a review for all the hypothesis testing we did for means. If we had, let's go back to this first side over here, and we were just looking at sample 1 itself, we could ask the question, do we have enough evidence to conclude that the population mean is greater than 7. And since 7 is down here, I'm going to be pretty confident that the population mean of that group is greater than 7. So in all of our tests, those are the two things that go into it. What difference do you observe? That's going to be in the numerator, whether it's x bar a minus some hypothesized mean. If we looked at 2 samples, the difference between 2 means, and if in this case where we had 3, we're looking at the difference between the means. How far apart are they? Then we're comparing that to how much variability. So these are measures of standard error when we look at the spread within each group. So what you'll see this called is, on the top, I'll call it mean square treatment, but you'll have, sometimes they'll call it mean square between groups, so between the 3 groups. And in these 2 problems, the mean square treatment or mean square between, whichever you want to call it, is exactly the same in these 2 problems, because we have sample means of 10, 15, and 20. If we just had 2 means and we were looking at the 10 and the 15, that's easy to see. They both have a difference of 5. But again, this variability within each group then is going to be, we'll call it now mean square error. We've been calling that standard error. So at least philosophically, this is the same kind of thing. Differences between means, or size of the effect, divided by, I shouldn't say size of the effect, divided by error. So you'll also see this called mean square within, because that's within each group. How much variability do we have? Okay, so this is the kind of just setup that you would have, and this really, though it doesn't have to be, you often think of analysis of variance in terms of some experiment that's been conducted. In fact, if you take a course in analysis of variance, a lot of the time they'll talk about design of experiments and that. So what we have here is just, we're looking at the impact of training on performance. We have 15 people. We assign 5 to each kind of training. Now in reality, you would obviously have more people than this, but we're going to work things out. Whether we entered numbers on a calculator or worked it out by hand, we don't want 50 numbers per group. So this is just to kind of get you, I guess, the thinking of it. And this is what the problems are going to look like, the data when you get them. When you get the data in a problem. So when you're taking the exam, when you see 3 columns of numbers like this, whether it's on the exam 4 or the final, you see 3 columns of numbers like this, it's going to be an ANOVA. And we're going to look to see if there are differences between the means. Now, a data set like this, it's pretty easy to see. If there were 50 numbers per set, you need to, with this, I think I can look at this and say, do you think there's a difference between program A and B, that you would conclude that there's a difference? Well, A and B both are mostly in the 60s and 70s. It's going to be difficult to see a difference there. But look at program C. All of those scores are less than the other 2. I'm going to guess right now that when we get to the conclusion of this, that what we're going to say is, don't do program C. The performance is a lot lower than the other 2. You can see if we were drawing this out with the other, that it might look like this if we drew box plots. Let's say that, again, it's not going to look exactly like this because I'm drawing the box plot as if there were a lot more numbers. But we might have something like this. where that median is somewhere around maybe 65-ish. I'm just guessing on that. That's not necessarily what it is. But on this one, we would have a box plot that looked like maybe like that. Maybe this median is a little bit higher, but there's a lot of variability. So when I drew those white squares around the other thing, we have a lot of variability in those. But group 3, it's going to look something like the mean's a lot lower. In this case, I'm just showing the median. Some programs will put an asterisk in here to show where the mean's at. But all I want to show you with the box plots is that this is clearly lower than the other two. And we can see that with, with a small data set like this. There's where the question is going to be is something like that. There's actually 2 parts to this. Do we have enough evidence to conclude that there's at least one difference between means? And then once we've done that, if we say that there is at least one difference, then we'll go on to try and identify which specific pairs of means differ. So if you can't show there's a difference, you don't even need to go to the second part. Because if there's no difference between means, then there's no difference between specific means either. It's like I said in this one, I'm going to guess that the answer to the first one is yes, we're going to be able to show there's at least one difference between means. And then when we get to the second part, we're going to be able to say that C is lower than the other two, both of the other two, and that we're not going to be able to conclude that there's a difference between the first two because the means are close and there's enough variability and overlap there. What I'm going to get at here is, at least for a lot of this, is the process is exactly the same. We're going to formulate hypotheses. Maybe you can guess at least what HO is. Mu A equal to mu B equal to mu C. That they're all the same. The research hypothesis is a little bit trickier. We'll get to that in a minute. Then we'll look up a critical value in an F table. And in one of the handouts I gave you, that it has formulas on the front. And the last couple of pages, one of them is called the F table. That will be related to that first question. Is there at least one difference between the means? And then when we get to the second question, the Q table will come into play. And you will have these formula sheets available on the exam. So I think there's little to be gained by memorizing those. I will say this, though. We're going to compute means and variances. I expect that you already know those formulas, and then I won't provide those during the exam. Well, anyway, we look up that critical value in the F table. Then we compute the F test. So when we get to the critical value, we're going to say reject HO. It's called the F test. Reject HO of F test. It's always going to be a greater than. And there are no less than minuses or anything like that. This is always a greater than. That's another thing that I think helps on exam 4 is that there's 3 tests, and 2 of them will always be reject if whatever the test statistic is, in this case F test, is greater than some point. The chi-square test, which we'll look at tomorrow, will also be that way. And when we get to the regression, it'll always be a two-tailed test. So no guesswork there. Well, anyway, we'll compute 3 things. That mean square treatment, in the example that we had at the beginning, that would be the differences between the 10, the 15, and the 20, between the 3 sample means. So just like we had x bar A minus x bar B in the numerator, looking at difference between the 2 sample means, now we're going to find a way to look at the difference between all 3 means at one time. Then we're going to compute MSE. That's equivalent to standard error. That's how much spread is there within the groups. So it's the ratio of those two things, the effect or the difference between sample means divided by the amount of sampling error that you have. And that's the Ftest, is just going to be the ratio of those two. Now the formulas for those are long. It takes a fair amount of calculation, but nothing that hard about them once you've done it twice. The first time you look at it, it's like, wow, it's just a lot of stuff. But like I said, it's fairly straightforward. Then you'll state your conclusion. Then if you reject HO, we'll just use Tukey's HSD test and not the Bonferroni intervals, unless we do it with a computer. But that's going to be the test that says which specific means differ from one another. Okay? And I'll just go ahead and say that that's one of the two places in this problem, and probably the most, where, if I'm just going to say flat out, if someone misses some points on this problem, there's probably about a 75% chance that this is where they miss it. It's not that hard, but obviously you should pay attention to the whole thing. But if you want to focus in and put the spotlight on something, once you have things down, spend a little bit more time with that last part. Okay, so the hypotheses will always be like this. There's at least, this is the HR or the HA, there's at least one difference between means. So it's not mu A not equal to mu B not equal to mu C. Because only one of those has to be true. HO is that they're all equal. So any one or more of those first three will make HO false. So the first part of the problem is there at least one difference between means? Is at least one of those three true? Then the second problem will be, if we did say one of those is true, one or more, then we'll try and determine which one or more of those is the case. So the critical value. We're going to compute 2 degrees of freedom. So one of those, K, is the number of groups. So we had 3 groups. We had program A, B, and C. 3 groups. So the degrees of freedom in the numerator will be K minus 1. In this case, 3 minus 1 is equal to 2. I'm going to make a correction here. For the denominator, that should have a T there, NT, for total sample size. In this particular problem, we had 3 groups with 5 observations in each group. Plus, in the beginning of the problem, it said we're going to assign 15 people. He has 15. He's going to assign to 3 groups. The total sample size is 15. K, again, is the number of groups. So 15 minus 3 is 12. So we're going to have 2 and 12 degrees of freedom. I'm going to show you where we get this in a minute. We're going to reject HO if the Ftest is greater than 3.9. Let me... Okay, here's an F table. Again, what you have in your possession right now. Along the top, we have degrees of freedom numerator. 2. Along the left-hand side, degrees of freedom for the denominator. 2 and 12 degrees of freedom. So there's your 3.9. We're going to reject HO if Ftest is greater than 3.9. So we got the degrees of freedom, 2 and 12. And we're only going to use alpha 05 in this. Okay. I would have to give you a separate page for each one. I've seen some that try and put, like every time we have one number here, they'll put 3. One for 01, one for 05, and one for 0.1. Yeah. We're just going to use 05 all the time. It's easy enough. Or it's the same process every time, so let's just stick with that. Okay, so the next thing you'll have to do is calculate the descriptive statistics and the grand mean. We'll go back and review that in a second. We'll just go ahead and put those problems up there. But for right now, let's just go ahead and say we computed the means of those 3 samples, and the means of those samples were 64, 70, and 46. We'll compute them in a minute, but for right now, let's just get to the main process here, or what's new. The grand mean, so this is X bar A, X bar B, and X bar C. The grand mean, I probably have this on one of the other slides, but let's go ahead and put it right here. We have everything on one page, is X bar bar. Read that, the mean of the means. So it's just X bar bar is equal to X bar A plus X bar B plus X bar C divided by K, the number of them. So I'm just taking those 3 numbers, 64, 70, and 66. And that's going to come out to be 60. If you just took all 15 numbers and computed the mean of them, it'd be the same thing. It's the mean of the whole data set. This is just, since we have the 3 sample means anyway, we're just going to take the average of those 3 means. Then we have sample variances. Again, I'll go back and do that by hand on the thing, but this is going to be S squared A, S squared B, and S squared C. So I'm just computing, it's just like standard deviation, just don't take the square root. Still going to be the sum of the square deviations divided by n minus 1, just don't take the square root like we've been doing when we calculated standard deviations. Actually, while I'm on this page, the way we're going to get that numerator, remember if it were just 2 means, X bar A and X bar B, we would just get the difference between those. That would be our numerator when we calculate a test statistic. The way we're going to get it, and you'll see in the formula in a minute, is we're going to get the difference between each one of these means and the overall mean. A little bit more to it than that, but that's basically what we're doing, is how far apart is each mean, sample mean, from the mean of the whole group. That's how we'll get the difference between means. We can't just do X bar A minus X bar B anymore because there's 3 of them. And then when we get the bottom of it, the mean square error, it's just going to be the average of those 3 variances. So we'll add them up and divide by 3. That will be the mean square error. Okay, so when I do it, that's what I do. I would compute the mean square error first. Did I skip a slide? Oh, wait, okay. The way I would work this by hand is, I'm going to have to go back and forth here. I would actually write this first. Ftest is equal to mean square treatment divided by mean square error. Then, the next thing I would compute is the MSE. To me, it's just easier to do it. So I take those 3 variances, get the average of them. that into the formula here. Put that into the bottom. That's easy enough to get. If you have the variances, just take the average of them. That's how you get to the denominator. Okay, so here's the one that looks messy. I told you we were going to get the difference between each x bar and the mean of the whole group. So you can see on the first one, the sample mean x bar A was 64. The overall mean was 60. I square that difference and multiply it by the sample size of that group. Okay? So again, this is just the sample size of the first group. There were 5 numbers there. This is just the mean of the first group. That must have been 64. And this is the mean of the whole data set, or the average of the 3. So once you just have that part, you just do the same thing for the other ones. Then you just repeat. For the second group, it's sample mean minus the overall mean. So we have 60 at the end of those, all of them. Then just the sample means. Square those differences, multiply by the sample sizes of each group. In here, when we calculate, I'm going to use the same sample size for every group all the time. And in fact, for some mathematical reasons, if you are designing an experiment, you should always have the same number in each group. You don't have to, but it turns out that the test works better. There are some assumptions for the test. Since right now we have small sample sizes, we would assume that we're sampling from a normal population. There's some other ones too, that equal variances like we had with the pooled. We're kind of assuming that that's true. But it turns out if you have equal sample sizes, those assumptions aren't as important as if you have unequal sample sizes. So anyway, that's a little bit beyond this class. I'm just going to say, if you have control over things, like if this were a production process and you could pick items from 3 different things and you decide how many to sample from each one, sample the same number from each one. If you have 15 people and you're assigning to training programs, don't assign 10 to one and 2 to the other and 3 to the other. Assign 5 to each one. If you have 150 people, 50 to each group. Well, anyway, then you divide by k minus 1. So we had 3 groups, divide by k minus 1, or 2. But of course that is the degrees of freedom for the numerator. I'm losing I can't see where there we go. I don't know if that helped or not. This is the only way I can find my cursor is to, oh well, lost it again. So then the Ftest is 37.44. Just take that MSTR that we just had, the 780, divided by the MSE. That's 37.44. That's greater than the 3.9 that we had for the critical value. Therefore, we're going to reject HO. We're confident that there's at least one difference between population means. To this point, we haven't said which one, other than we could tell at the beginning because we had so few numbers. But in this process, we haven't said which ones are different from which other ones. All we've concluded is that there's at least one difference between population means. Remember, our HR was our HA or HR, whichever you want to call it, was at least one of these is true. at least one of those is true. All we've said now, when we reject HO because 37.44 is greater than 3.9, is at least one of those is true. And we can say then that type of training has some effect on productivity. And we don't know which training program is better or worse than any of the others. We just know that there is a difference. And once we know that, then we'll go to the next step and say which one or more, which differences are they? Is it this one? Is it this one? Are both of those true, but this one not? And that's what we'll use when we do it by hand is the Tukey's HSD test. Okay, so here's the Tukey's HSD test. And I've already said this, and it bears repeating, that there are two places on this one. I'll show you the other one in a minute, where I know most of the errors occur on this problem. And this is by far the part that gives more people trouble. It's not like everybody has trouble with it. I mean, most people get it correct. But if there's going to be a problem, this is the area. So there's really a three-stage process in this. The first two you can do in either order. Okay. I'm going to start here and say, get the difference, the absolute value of the difference between each pair of means. So our first sample mean was 64. For group B, it was 70. Those differ by 6. That's just like X bar A minus X bar B, but we're just doing absolute value of it. Notice we were squaring everything when we went through. Then X bar A minus X bar C, 64 minus 46 is 18, and then 70 minus 46 is 24. So step one, find the differences between each pair of sample means. We're only going to do 3 groups, but you could have 6 groups, and you can imagine that this would get a little bit more complicated the more groups you had. But the thinking is just the same. So that's how far apart are the sample means. HSD, which stands for honestly significant difference, is how far apart do the sample means have to be before we conclude that the corresponding population means are different. So these are how far apart. This is going to be how far apart before we reject HO for each one of those specifically. So MSE, we calculated that a minute ago. It was 20.83. Remember, we used it in the denominator for the Ftest. So we already have that. NG is the size of each sample. Okay. This particular test, the way we're using it, assumes that the sample sizes are equal for each group. In this case, we had 5 in each group. So that one's pretty easy to get to. Okay, so for Q, we'll use the Q table. So I've given you 2 tables, the F table and the Q table. And the degrees of freedom in the denominator is the same that we had for the F test. Remember, the total sample size minus K, or 15 was our total size, minus K was 12. So that's exactly the same. The degrees of freedom for the numerator is just K. Don't subtract the 1. That's not my fault. That's just the way the table is set up. The F table is based on K minus 1. The Q table is just based on K. So in this case, K is 3. And so the degrees of freedom, the numerator will be 3, and so we'll be looking for 3 and 12. So here's the Q table. It works just like the F table. Except for we have 3 degrees of freedom in the numerator and 12. So that's 3.77. And there's our 3.77. Multiply that by, again, the square root of 20.83 divided by 5, you get 7.69. I have to be honest here. I have no idea why people find that difficult. I just haven't been able to figure it out. Get the difference between each pair of sample means. They were 6, 18, and 24. How far apart before you conclude that there's a real difference? 7.69. So what I did, and what I normally do, is go draw an asterisk next to the numbers that are greater than 7.69. And then, since I have X bar A and X bar C right here, that means that I can conclude that mu A is not equal to mu C. And I can conclude that mu B is not equal to mu C. Since 6 isn't bigger than our, if you want to think of this as a critical value, mu A could equal mu B. Now remember that when we were looking at it, we could tell that the mean of the third group was 46, the sample mean. So what we can really tell here, just in a practical sense, is that C is different from both of the others. C has a lower mean, therefore we just shouldn't use C. If it comes down to A and B, we can't say the two means could be different. The difference between the 64 and the 70 could just be random error. So if we want to decide between A and B, we should use some other criterion. Not this. You guys have questions about this one? Again, before you take the test, assuming, and I think you will, you'll have everything else down pretty well. Come back and spend a little bit more time on this. It's the spot, I'm going to say, of everything on this test. This is the most frequently missed points, by far. My hope in saying that, or my intent isn't to scare you. It's my hope is that you'll pay more attention to it and nobody will miss it. My goal, which I've been unable to meet in 30 years, is for everybody to make an A. It's happened in some of my classes, never in a stat class, but I do not feel compelled to, how should I put it, artificially say that some people have this grade and some people have that. You get what you get. Okay, so in this one I happen to use Bonferroni intervals. Tukey has a similar kind of thing, but it's really just the interpretation I want to get at anyway. So this is the way a computer, or at least one way a computer will generate results for that second part, which specific means are different. And so if we were looking at a confidence interval between just two means, what do we look for? on the test we just took. We look to see if the interval includes 0. If there's 0 in there, there might not be a difference. There might not be a difference between means. So I'm going to look at A and B. And the confidence interval is over here. That confidence interval includes 0. Mu A could equal mu B. Then I'm going to look at A to C, and I look at the confidence interval. It's about 10 to 26. Doesn't include 0. There's a difference. And look, A, what this says is A, we think is somewhere from about 10 to 26 points higher than C. And then I'm going to go to B and C. I'm not going to do B and A because I already did A and B. And I get about 16 to 32. So I think that the population mean for B is between 16 and 32 points higher than it is for C. And that's it. It has 6 comparisons there. If you don't want to do those 3, do the other 3. I mean, we've got, in this case, B to C. If we had done C to B, it's just the reverse. We would say that C is somewhere between 32 and 16 less than B. So it's just the order that changes. So bottom line, if I were doing this, I'd just do the first 2 and skip 1 and do the B to C. You really are only making 3 comparisons. They just here reported in both directions. Questions to this point? Then let's go back. Sure, I don't think well, I've already said that. Okay. I'll get there in a minute. Maybe. Here we go. That's where I wanted to be. I just wanted to compute the means and the variances for these. So this part isn't new, but it's part of the problem. I will say this. I'm likely on an exam to just give you the means and the variances for 2 of the 3 groups. I'm going to compute it 3 times and all of it for this one. But on an exam, I probably would just give it to you for 2 of them and have you do it for the other one. Part of the reason I'm going to do this is, we have exam 4 followed up 24 hours later by the final exam. And so this is review, computing the mean and the variance. Okay? At least that's the way I look at it. So the first thing will be, and I didn't bring a calculator with me today, so maybe you guys can check my work here. The sum of those what I wanted. I'm going to say is 320. Am I right? So the mean of that first group is the sum of the x's divided by n, which is equal to 320 divided by 5, and that's 64. You guys verify. I think the mean of the next one is going to be, the sum is 350. And I'm going to think here maybe 230. I should have put here x bar A, and here x bar B. I'm not going to rewrite the formula. I've already done it once. 350 divided by 5 is equal to 70. And x bar C equal to 230 divided by 5 is equal to 46. So remember in the problem, those were the sample means that we had. So we're just computing the mean of each group. And to get the variances, I'm going to actually write this over here to the right. It's going to mess up when we get over to C, but S squared, that's the variance, not S squared, divided by the sum of the squared deviations divided by n minus 1. So remember the standard deviation, we just had S, and we would take the square root of this. I started off this lecture with saying there are two places where people are most likely to miss points on this. This is actually the other one. We've been taking the square root all season, all semester. Therefore, someone will take the square root of this. I have no idea why, but sometimes people divide by n instead of n minus 1 on this. So of all places to make a mistake, it's on something we've been doing and it's not that hard. So that one I don't think is something, I don't know. I assume that you really don't have to study a lot to know that. You just have to focus when you take the test. That I'm not going to take the square root and I'm going to divide by n minus 1. So for program A, I'm going to get the deviations. I'm going to subtract 64 from each number. And of course the sum of those will be 0. Then I'm going to square those. It's supposed to be an I down there. I get that to be 80. So for S squared A, I'm going to have 80, the sum of the squared deviations, divided by 4 is equal to 20. Is that what I had on the PowerPoint? Did I? Okay, good. I don't have my calculator with me and my memory's not, I haven't memorized all the numbers in here yet. So for B, x of I minus x bar and x of I minus x bar squared, except for I'm subtracting from 70. That sums to 0. That looks like 50. So S squared B is going to equal 50 divided by 4. It's 12.5. And then for program C, subtract 46. That's 0. Square them. It's like 120. So S squared C is going to equal 120 divided by 4, and that's 30. So again, when we computed MSE, it was just the average of those three. We computed X bar bar. It was take the average of those three sample means, the 64, 70, and 46. Then in essence, just get the difference of each one of those, the 64, 70, and 46 from the overall mean. Have I jogged your memories on computing means and variances? I believe way early in the class I said for most of the course we'll compute standard deviations. We'll just have the S's and take the square root. But I believe I don't know, foretold, warned, whatever, that there would be a point in which we would do the variance. Of course, when you get to something called analysis of variance, there's a big clue that you're going to compute the variance. Okay, one more thing on this. If you would take out your statistical calculators and go to Stat and Edit and put these numbers in list 1, these in list 2, and these in list 3. And I'll tell you, on exam 4, I'll have you work through this by hand. I may give you, for example, I might give you the means for groups A and B, the 64 and the 70. I might give you the variances for groups A and B, the 20 and the 12.5. Ask you to make those calculations for group C, the mean and the variance, and then to go through, compute the MSE, the MSTR, the Ftest. Then if you reject HO, to go on to the Tukey's HSD test. Can't get check figures for everything, but we can get check figures for Ftest, mean square treatment, and mean square error pretty quickly. Can actually get check figures for the individual variances as well. A little bit more to that. Well, anyway, now add those numbers in there. If you would do stat, tests, and then if you would just hit your arrow key one time up, that'll go to the bottom of the list, and the last thing on the list is ANOVA. Okay? So just select that. And now you come to a screen that just says ANOVA and it has open parenthesis. L1, comma, L2, comma, L3. Remember the L1 is just second one, and the comma is about the third or fourth row down, sort of in the middle of your calculator. No, I guess it's on the second column, fifth row. And then, at the top of that, you should see the Ftest, which should equal whatever we had. Then you'll see, does it say factor? Yeah, the p-value. That would be the p-value. So if HO is true, there's that chance that we would get these data. Then factor, that's the same as treatment. And you're going to see, I don't care, for whatever reason, if you look at different books or different programs, you'll see factor, you'll see treatment, you'll see between, you'll see group. When you get to the error, you almost always call it error, but occasionally you'll see someone, a program or a text that will call it within. Well, anyway, under factor, you will see degrees of freedom is equal to 2. That's k minus 1. Then you'll probably say SS, sum of squares. Don't worry about that for now. Maybe not even in this class. And then after that, it should say mean square. That's the mean square treatment. And I can't remember what that number was, 780. That's what we had a minute ago. So now, you can check to see if you have the mean square treatment and the Ftest correct. If you would arrow down, you will see the degrees of freedom for error, and you will see the mean square error. And that should be, I remember that one for some reason, 20.83. And those are the degrees of freedom we used when we looked up the Ftest to get the critical value, the 2 and the 12 for degrees of freedom there. Well, let's say that you put those in there and it doesn't match up. So you want to now find where your calculation error was. What I would do is go to Stat, Calc. Now, this is assuming you made a mistake. If you came up with this same mean square treatment, mean square error, and Ftest, well, you probably didn't mess up calculating a variance or anything. But if you would go Stat, Calc, and then if you just hit Enter for the one variable stats, and then put L1, then you should get the mean. X bar will be there, and it should say 64. And it gives you the standard deviation. So what you would need to do is take the standard deviation that's on there, whatever it is, type that in and square it. And if that's 20, you didn't mess that one up. Then just repeat that for L2 and L3, and you can check your means and your variances. Again, it gives you the standard deviation, so you'll have to square it to see if you got 20, 12 and a half, and 30. And if you got those right, then you messed up one of the other ones. Of course, if your MSTR is wrong, then you know it was somewhere in that formula. It would either be calculated the variance wrong, or you miscalculated that long formula for the MSTR. Again, that's just troubleshooting if you come up with the wrong answer at the end. Questions? Problem sheet that I gave you, the one that says ANOVA on the front of it. Okay, that first one there, let's make that the homework problem. I will also actually do this. Number one, you should work and keep. I'll post a key for that problem. Okay? I happen to have it right here. So I'll post a key to problem 1. I can scan that and put it in right after class. So you can work that one for practice. Make sure you have it right. And then your homework will be problem 2. I don't see if you work one of these and check it, then work another one, yeah, you should have this down. As I said, it's long but straightforward. If you would look a little bit further through here, we're not going to work this now, but I just want to make sure you see it. If you would look at problem 4, notice that in that problem, the sample size is already given, the sample means are already given, the sample variances are already given. Therefore, MSE will just be the average of those 3 variances. To get the mean square treatment, you'll have to get the mean of those sample means and then just compute through that formula. What I'm going to get at is that if I give you those values right there, obviously the real numbers aren't there anyway, so you couldn't compute them, but I've worked half of the problem. On problem 6, I want you to see, and I guess we'll talk a little bit more about this maybe tomorrow, but I want you to see how ANOVA results are typically presented. So on problem 6, for some reason problem 5, it should just be part B of that problem, but anyway. So problem 6, the tennis racket problem there, there are the means and the variances. And instead of doing any calculation, I put what's called the ANOVA table. And I'm not saying there wouldn't be any differences, but this is the way ANOVA results get reported. That between groups, sometimes it'll say treatment. SPSS apparently calls it between. Within is the same thing as error. You can see the degrees of freedom, 2 and 27. And you can see the mean square. The 830 would be the treatment. The 62.5-ish would be the mean square error. If you divide mean square error by mean square treatment, the 830 by the 62.5, you'll get 13.281. And then there's your p-value. I am going to have you, my plan is to try and cover both the regression and the chi-square tomorrow. Then next week we won't have any new problems. We'll start doing some stuff on the computer. That's actually, I think we've got a few minutes. I think I'll actually just pull up SPSS and just do something really quickly in a minute. But right now, just looking at that, then you'll see the confidence intervals below that. That's the part I already showed you. Look to see if the intervals include 0. So why don't we, I think probably this will be the thing to do. Look at the number 1 on your sheet, the one that I'm telling you to practice on. And give me a second here. If you're on campus, probably the program you want to use, I'm going to show you 2 programs. SPSS is a package program. It's good. It's expensive, though. If you use this, you're going to be either on a college campus somewhere or at a company that bought the program. There are several good stat packages. SPSS is one. We would have to go through the server. There's another one called Stata. What I'm saying is, if you get out of school and you need a program, Stata is a lot cheaper. That's all I'm going to say. It works similar to this. R is free for any purpose. So that's one of the reasons I'll show you at least a little bit about R in here. It's a little harder to use starting out, but I still want to show you because it's free. Well, anyway, on the computers on campus here, if you go under the business folder, IBM statistics, and then just click on it. It takes a few moments to load. It's a very large program. I'm hoping that it's loading. Yeah, it's loading. Got my little... There it comes. I'm just going to click on New Data Set. And what I want to show you before we actually put any numbers in is down at the bottom left, you'll see Data View and Variable View. Data View, that's where you put the data in. And Variable View, you can put variable names and change the properties of things there. So for the data view, I'm just going to go up here, and I'm going to enter the numbers for the problem. Now, each row is one individual. So for the first person, I'm going to put 83, and instead of A, I'm going to put 1, group 1. So I'm going to put all 15 numbers, the 83, 84, 74, 91, 78, and just keep on going. 71, 80, 87, 76, 71, 95, 91, 85, 92, and 87. Group 1, 1, 1, 1. Of course, if you had a bunch of these, you'd want to use copy and paste, but there aren't that many here, so I have two variables in here. The variables are productivity or something like that. Yeah, productivity. And the other variable is what kind of incentive plan? Okay? A, B, or C. What I'll see people do, they'll come and say, well, I can't get this to work. And the reason they can't get it to work is because they put the first 5 numbers in one column, the next 5 in the next column. But each row, and then each row is just one person. So when we get down to observation 10, that's a score of 71, group 2. That's that person. That's the information I have about that person. Now I'm going to go, I don't like the names var1 and var2. I'd like something a little more descriptive than that in my output. So I go to the variable view, go over here, and I'm going to put when you name these here, you can't have any spaces, special characters, or anything like that. So I'm just going to put plan here, and I'm going to go over label, and I'm going to say incentive plan. So in any kind of output that I have, this is what I want. This is the label I want it to put. I don't want to just say plan. I could have called those X and G or whatever, and then just give labels here. Now when you have the productivity, that's just a quantitative numeric variable. But plan, and you really don't even have to change it over here, that 1, 2, and 3, and you can leave it like that, but I'm going to do something a little bit different here just to show you. I went over and, let me start back over on that, under values, And for my categorical variable, I just click there and you see the 3 dots come up. And I'm going to say, when the value is 1, I want it to say plan A. Add. When it says 2, I'm going to put plan B. Now one of the reasons you do it this way is when you're entering data into a computer, remember with 15 observations is not that bad. It's easier to put in 1, 2s, and 3s than it is letters or words or something like that. So I put in the 1s, 2s, and 3s, and I just go over here and say what I want those to say on the output. And again, I couldn't have, in my data, I couldn't have had any spaces or anything. So this is going to make it just look better also. And you have to, if I clicked OK right now, I would get an error. I'll just show you. Didn't put in my last ad, so just click OK. I should have said cancel. And then it would have taken me back here. I'm going to put plan C again. Add. Now they're all 3 over there, and I can click OK. Okay, so I have data view, variable view. Data where the data's at, variable where I can make changes to the variable. There's some other things you can change, but that'll be enough for in here. Okay, from there, it's pull down menus. And you can do that from either view. It doesn't make any difference. By the way, you see right here where it's got that 1A thing? Watch what happens. If you want to see what it is on there, you can. But anyway, under Analyze, a couple of things I'm going to show you. First of all, let's go to Descriptive Statistics and Explore. Analyze, Descriptive Statistics, Explore. And dependent is the variable I'm trying to predict, productivity. Incentive plan is the factor or group or whatever you want to call it. I'm going to say you can either display statistics or plots, and you can go and make some changes in that, but let's not do that for now. Just click OK. And you can see now, first of all, it tells me that I have sample sizes of 5. There's no missing data in the thing. If you had missing data, you would just put a period in there. But then after that, it tells me more than you would ever want to know. It has the mean, the confidence interval for the mean, the trimmed mean. We haven't covered that here, but what that is, by 5%, that means if you have extreme values, it just trims and gets rid of the top and bottom values, and so you get the mean without those extreme values. The median, the variance, the standard deviation, and some other things. We haven't covered it in here, but it has something that measures skewness, and it has one, kurtosis is how flat the distribution is. And then there it is for Plan B and Plan C. It gives you stem and leaf displays. It gives you box plot automatically. In fact, I'm going to go back and do one other thing. I'm going to go back, Analyze, Descriptive, Explore, and under Plots, I'm going to check Histogram. I'll just run that again. There's all the stuff we already had. Now I have histograms for all 3 data sets. And then there's that. I guess I don't even know if I really want to. I'm going to show you one other thing while I'm at this point. And it's because I don't like that color. I just don't. So I'm going to double click in there. Open an editor. All I have to do is double click on the part I want to change. And let's say I like light blue. Change it. You can double click in the background here, and where it says fill, I'm going to put no fill because I value my ink and I don't want to have have it putting gray ink in there. In fact, I probably wouldn't use light blue. I might use white. Make sure if you do that, don't say no color. It'll make your graph look funny. If you put white, then it's still not going to print anything. So if you're using your own printer, you can get rid of the colors and stuff like that. Okay, so all of that was under Analyze, Descriptive, and Explore. Analyze, Descriptive, Explore. Then just move the variables over. Okay, so Analyze, Compare Means. And notice that what we have on there is means. Really, I don't use that very often. One sample t-test, independent samples t-test, paired samples t-test, and one Way ANOVA. In other words, the first three of those are the problems that we just covered on the previous exam. We had the one sample t-test. We had an independent, that's two separate groups. And then we have a paired sample t-test. And then we have one Way ANOVA, which is what we're doing right now, so I'll go ahead to that. And productivity by incentive plan. And there's your ANOVA table. As the between and the with groups. You can see that the significance, where it says SIG, that's the same thing as p-value. I think SPSS might be the only program that I know that calls that SIG. Everybody else calls it p-value, which it is. But I'm going to go back and say Analyze, Compare Means, ANOVA, Post hoc. That means after the fact. Part A was, is there at least one difference? Once we've done that, and you could have done this right at the beginning anyway, I'm just going to check Tukey. We could have selected Bonferroni too. That's what I did apparently before. Continue and OK. And now in addition, it reruns the ANOVA and puts that. But then we get actually two things here. These are two ways of presenting the same thing. So we saw with that small p-value that we rejected HO. So I'm looking at plan A and plan B. It goes from about -5 to +15. Includes 0. Mu A could equal mu B. The interval includes 0. Plan A and plan C, -18 to +2, about. That includes 0. Mu A could equal mu C. So that was A to B, A to C. Now I'm going to go B to C, and that goes from I should circle that one too. Those are the three. -23 to -3. 0 is not in the interval. Mu B is not equal to mu C. You might also note that, it has an asterisk by it. It also has p-values. You can look at the one that's less than 0.5. I kind of like for you to look at the confidence intervals because that kind of, again, is a review of what we've just done. Does the confidence interval include 0? If it includes 0, they could be equal. If it doesn't include 0, they're different. In fact, what you would say here is that plan B is somewhere from about 23 and 3 lower than plan C. So you can go back and look at the problem, but what that means is that, and I'm pretty sure that this is right, it was productivity, that I would prefer plans, that I would avoid, if it came down to B and C, go with C. Between A and B or between A and C, coin toss. Find some other criterion to use. Tukey's test also presents the same result in a different way. So here's what the way to read this. It has BAC. B and A are in the same column. They could be equal. C and A are in the same column. They could be equal. But B and A, we don't have them together. B and C are not in the same column. C is not in this column and B is not in that one. Those are the ones that differ. So you can look at that one. I usually just look at the intervals. I don't know. If I had a lot of plans, I might just look at this. It might be easier to see.